Okay, so our next result is this lemma 445. In the previous video, we saw one other lemma like this, lemma 444, which states that any orthonormal set of vectors in an inner product space is linearly independent. Here also we have an orthonormal set of vectors, but now something else is being stated. Besides the set, we are considering some other vector w. This w of course may be one of these also. And using these things, another vector u has been constructed as a linear combination of w and all the vi's, specifically this, in which from w we are subtracting this multiple of vi for each i, where the coefficient scalar is the inner product of w and vi. That's how we get a new vector u in V. Now the statement is that this u is orthogonal to each of the vi's. So let's see the proof. The proof is just very straightforward. You need to prove that u is orthogonal to vi for each i. That means you have to calculate the inner product of u and each vi. That should be 0. That means orthogonality. So the proof goes like this. For any integer I in this range, we have this. Okay, so we want to calculate this. Now in place of u, we are going to write what it is. So u is w minus the inner product of w and v1 times v1 minus v2 minus, and in the middle somewhere we have this ith term also. Although I say in the middle, but you understand that this I may be 1 also. So it's a general case. Vn. So this is what u is, and then we write the second component, vi. Okay, now using the axioms for our inner product function, this just becomes w comma vi minus w comma v1. First of all, we are just going to write all the things down, and then we will see what comes from that. v1 comma vi minus w comma v2 comma vi minus vi comma vi minus, and finally the last term okay. Now note that so far we haven't used the hypothesis that the vi's form an orthonormal set. Now we are going to use it, because now we have this kind of inner products. So using the fact that the vi's form an orthonormal set, these inner products will all have value 0 except this one which has value 1. That is because if I is if I is not equal to 1, then this has to be 0, because v1 and vi being different vectors from that orthonormal set are orthogonal to each other. Similarly, this is going to be 0. All of them will be 0 except this one, which is 1, because vi has length 1. So ultimately this expression becomes w comma vi, the first term, and among the rest of the terms only this one survives, which also turns out to be this same thing. So that's how we get 0. Hence u is orthogonal to each of the vi's. That's it, that's the proof. Now, based on this kind of construction of u using the vi's and w, we are going to see this next result, which is very important and kind of central to the theory of finite dimensional inner product spaces. So because of its importance, it's a theorem and not just simply a lemma. So the statement is just this: let V be a finite dimensional inner product space. Then V as an orthonormal set as a basis. Okay, so V is a finite dimensional inner product space. So because of the finite dimensionality, we already know that V has a finite basis. But the theorem claims that we can actually find a basis which is also an orthonormal set of vectors. And let's now see the proof. So the construction of the orthonormal basis, if we call it that, is itself, it has a name. It's called a Gram-Schmidt orthogonalization process, which appears in many places in mathematics. So let's see what the proof is. So let us first consider the case where V is the zero space. That means it has only one vector, nothing else. If V is the zero space, which we denote like this, then its basis is the empty set. We already know that this is the case. When you are dealing with the zero space, this set consisting of just that object, that zero vector, spans V, but this is not a linearly independent set because it has the zero vector in it. But this also spans V and it is linearly independent, so this is the basis. And in fact, it also matches with the notion of dimension. I mean, the zero space is considered to be zero dimensional. It's like a single point, which is the cardinality of the empty set, 0. And this is an orthonormal set of vectors. Okay, but why orthonormal set? I mean, how is it orthonormal? Let us try to understand that. Not one more thing, that you cannot just simply ignore this case, because this is also a legitimate case. The zero space is also a finite dimensional inner product space. Oh, and if you ask what the inner product is in this case, then that inner product is just simply this. Since you have only one vector, you need to define only this, and you can define it to just be the complex number 0. That's it, and that itself is the definition of your inner product. Okay, so let us now see why the empty set is an orthonormal set of vectors. What do we need for orthonormality? A set of vectors is said to be orthonormal if two distinct vectors from the set are orthogonal to each other and each vector from the set has length 1. So if you write these things down in symbols, it will look like this. If U and V belong to the empty set with U being different from V, then the inner product of U and V is equal to 0. If this condition is true for all U and V in the empty set, then the empty set is an orthogonal set of vectors. And for normality, you just similarly have that other thing. If U belongs to the empty set, then its length is 1, which itself is equivalent to the inner product of U with itself being 1. Now note carefully that both of these statements are actually implications, which are vacuously true, because the hypothesis of the implications in both the cases are false. So the implications are vacuously true, but true nonetheless. That is why the empty set is in fact an orthonormal set of vectors. So in this case, we have what we want. Now we can see the other cases. The other cases means now we can go to non-zero vector spaces. Now, assume that V is non-zero. Let the dimension of V be n. So now n is a positive integer, not 0. Let V1, V2, etc. Vn be a basis of V. We know that it exists, at least one such basis exists, because the dimension of V is n, and n is a finite number. It's a natural number, positive natural number. Okay, but this itself may not be an orthonormal set. We want to have an orthonormal set also as a basis. So now using this we have to create an orthonormal set, and the process of doing that is the Gram-Schmidt orthogonalization process. Okay, so let us start that in the next paragraph. Define W1, a vector W1 to be the vector V1 divided by its length. Now when we say a vector V1 divided by its length, it actually means you are considering this scalar multiple of V1. Division is defined in terms of scalar multiplication. It has no other meaning. And one more thing, how do you know that this is non-zero? That you should also be careful about that, because otherwise it will be meaningless. The non-zeroness of this norm of V1 or the length of V1 comes from the fact that V1 itself is a non-zero vector, which in turn comes from the fact that this is a basis, and as such it's a linearly independent set, so it cannot have the zero vector in itself. So now we have to write these things. Note that since V1 is a basis vector, we have V1 not equal to 0, and so its length is also non-zero, and that's why W1 exists actually, and W1 is a vector in V. Okay. Next, now we are going to define another vector using W1 and V2. Now define U2 to be V2 minus the inner product. If I want, I can write W1 first, but let me write the V2 itself first. Okay, suddenly why we are considering this, it will be clear now. There is a reason for considering this. Two reasons actually that will now be clear. Okay, so the first thing to note about this vector U2 is that U2 is not equal to 0. Let's see why. Once more, you just see what U2 is. From V2, we have subtracted this multiple of W1. W1 is this vector which we have. Perhaps I should have written another thing about W. Okay, I will write it afterwards. So from V2, we are subtracting this multiple of W1, where the coefficient scalar is the inner product of V2 and W1. So you can see that it's like what we have already seen in the previous lecture. Note that U2, which is V2 minus this W1 is equal to, so now let's write what W1 actually is. V1 divided by its length. So that just simply becomes this. So you can see that U2 is actually a linear combination of V2 and V1. Which is not equal to 0 since this is a linearly independent set. Okay, why? What is the reason for that? We know why this is linearly independent, because this is a basis for V. So this set itself is linearly independent, so any subset is also automatically linearly independent. Okay, but how does linear independence of this imply that U2 is not equal to 0? That is because you see that U2 is a linear combination of V1 and V2. So such a linear combination due to linear independence would be 0 only when the coefficients are both 0. What are the coefficients here? We have one coefficient minus of this inner product divided by the length of V1. We don't know whether this can be 0 or it cannot be 0, but the other coefficient is 1, which is not equal to 0. That is why U2 is non-zero. So we can define a vector W2 now. Here we define W1, that's where the process starts. Now we are defining W2 to be U2 divided by its length, just like this one was V1 divided by its length. Okay, so now we are going to note some things about W1 and W2. Some things that are true about these vectors, and also one thing that is true about them together. That is, what I am trying to say is that W1 has length 1, W2 also has length 1, and W1 and W2 are orthogonal to each other. Note that. So the fact that W1 has length 1 is what I wanted to say there, that I should have written there itself, but we can do it now also. Okay, so to find its length, we just find its norm or length. How would it look actually if we write what W1 is in fact properly, really properly? Then it is this. But you already know one thing about vectors in an inner product space, that for a vector V and scalar alpha, the length of alpha V is the absolute value of alpha times the length of V. We have already seen how that is true. We are now going to use that here. Now, in place of alpha, here we have the reciprocal of the length of V1. Since this is a positive real number, it's a positive real number because its length, it's not also a general complex number, it's a positive real number. So we can just simply bring it outside as such without having to write another absolute value sign, because its absolute value is itself, and we are left with this part. So you can see that this is actually equal to 1 because they cancel out. So this is one thing. Similarly, this is also 1. You know why? Because it also has the same form as W1. And And now comes the other important fact, that this inner product is also 0. For this we of course are going to use the definition of W2 itself, but keep in mind W2 is not just simply that linear combination, but this in fact. So let's just do it in steps. Using one of the axioms for inner product, we write this step, and then I think instead of writing the things like this, let me write it as an equation array. U2 W1. So first of all, this scalar comes out. And then we write what U2 is. Not here because this serves no purpose other than just simply being here. So U2 is V2 minus V2 comma W1, W1 and W1. So now if we use the other axiom, then we just get V2 comma W1 minus V2 comma W1 times W1 comma W1, and this is where this fact is not going to be used, because the length of W1 is 1. So its square, which is this, is also 1. So that means we have V2 comma W1 minus V2 comma W1, and that of course is 0. 0, okay, 0 means now once you calculate, you see, never forget where you are and what the objects are that you are dealing with at every step. The moment we have all these things, we are now dealing with complex numbers. That's it. So this is just ordinary complex number 0, or real number 0 also, if you want to say it that. So now, okay, so at this stage, what are the things that we have obtained? We have obtained a vector W1 which has length 1, another vector W2 which also has length 1, and W1 and W2 are orthogonal to each other. So now what is the next natural step? To take the next natural step, we have to define another vector. Similarly, let's see what similarly means. Next, define U3. Okay, so to define, you can now probably see a pattern. W1 was defined using V1. To be this. W2 at once has not been defined, but it has been defined in steps. First we defined U2. U2 is defined using V2 and W1 of course. in this way, this form makes sure that the W2 that you are going to define from this is going to be orthogonal to W1. You may ask, how am I supposed to remember these things? I'm also going to say something about that, but right now let's just see the process. So this form I am saying makes sure that W2 is ultimately going to be orthogonal to W1. Exactly why, that we have already seen in that lemma, in the previous lemma. But in order to have another vector whose length is also 1, just like W1, we divide it by its own length. So now if you follow these steps and naturally write U3 next, then U3 would also look something like this, in which from V3 you will now have to subtract multiples of W1 and W2. Okay. So now the first job to do here is to realize that just like U2 was a non-zero vector, U3 is also a non-zero vector. Here the calculation, if you can do it mentally, you are welcome to do that, but I cannot do such mental calculations. Instead, just for this one, because after this we are not going to write U4 or anything. By the time we finish all these things with U3 and hence W3 that we are now going to define using U3, we will say that using this pattern one can go forward and one will get what one gets. So let us now first see that U3 is ultimately going to be a linear combination of V1, V2 and V3. Let's see how. We already have V3, so V1 and V2 are going to come from these two. Note that U3, which is W2 is equal to V3 minus, well, this term is just simply V1, okay, but then minus V3 comma W2, and if you write what W2 is, it is U2 divided by its length, and U2 itself is V2 minus V2 comma W1 times W1. Okay, so if we write the things in a somewhat nicer form, comma W1 divided by the length of V1 times V1 minus this times this, that is minus, what will it be, V3 comma W2, this inner product divided by the length of U2 times V2, minus minus, this one becomes plus V2 comma W1 divided by the length of u2. But now if you want to avoid writing another line which is almost like this, you can in fact write what w1 is, and w1 is v1 divided by its length. So you can see that now you are looking at a linear combination of v1, v2 and v3. You have v1 here, one term which is a multiple of v1. Another term here, if you want you can write these two things together, which I won't do. And you have a v2 term here, you have a v3 term here. So just like before, you can write which is non-zero. Non-zero means it's not equal to the zero vector. Since the set consisting of these first three vectors from our original basis is a linearly independent set. Again, why? Because we know that this is a part of a basis, so it's linearly independent. And because of its linear independence, and because of the fact that the coefficient of v3 is not equal to 0, so this linear combination cannot be 0, and that is why u3 is non-zero. So we can now define w3 to be u3 divided by its length. So that makes w3 itself have length 1. Thus, which we can just immediately conclude. But the important fact is that just like w1 and w2 are orthogonal to each other, w3 is also orthogonal to w1 and also w2. So w3 has length 1. Also, if we calculate the inner product of w3 and w1, so that becomes equal to v3 comma w1 minus v3 comma w. So you are practically seeing this calculation once more. The other time you saw this in the proof of the previous lemma. So that lemma, in fact that u tells us, you see, you can remember that there also we called that vector u. So here also we are calling such similar things u. And oh, see, I made a mistake. I realized this because w3 is exactly not equal to this. But instead, w3 is u3 divided by its length and then its inner product with w1. Minus and w1. So it's very easy to make such mistakes, but a small mistake can change many things. So V3 comma W1 minus V3 comma W1 times W1 comma W1 minus V3 comma W2 times W2 comma W1. So you can see that this becomes 0 because W1 and W2 are orthogonal to each other, and this becomes 1 because W1 has length 1. So ultimately we are left with this, which becomes 0. And a similar calculation would also show that W3 is orthogonal to W2, which of course I am not going to do. We can just simply mention that. So this is equal to 0, and similarly these two are also orthogonal. Their inner product is 0. So now we have added one more vector to our list, W3, so that the vectors W1, W2 and W3 each has length 1 and they are mutually orthogonal. If you choose any two of them, they are going to be orthogonal to each other. Proceeding like this, we construct a set of n vectors that is orthonormal. Note one thing carefully, that to construct each Wi, we actually need a vector Vi, a fresh vector Vi from our original basis. And that is why, since we have n number of such Vi's, we have been able to construct, or I mean if one continues this process, of course, depending on what the value of n actually is, one would end up constructing such a set of vectors that is orthonormal. Okay, so this much is guaranteed by the process, by the pattern of the process. Now, by the lemma from the previous video, since this is an orthonormal set, it's going to be linearly independent. This is linearly independent, but it's a linearly independent set of n vectors in a vector space which has dimension n. So that means it's the largest possible linearly independent set, and that's why it would also span the space besides being linearly independent, which is why this would be a basis, since the dimension of V is n, the set is a basis of V. That's it. That's what we wanted. We wanted to find a basis for V or a basis of V that is an orthonormal set of vectors. The previous one is also a basis, but this one has that extra property that it is orthonormal. Okay, so now some intuition as to why you, for example, I'm coming from the previous lemma. In the previous lemma, we were given an orthonormal set of vectors. Why is it that this vector is orthogonal to all the vi's? We have seen why that is so algebraically by computing the inner product, but is there something else about it that we can recognize much more clearly? Is there something about the form of u that tells us that yes, because of this fact, it's going to be orthogonal to all the vi's? You see, the notion of vector spaces comes from many sources, concrete sources, right? And one of those sources is actual geometry and actual physical vectors. And in fact, the word space itself makes it sound like it is something geometrical. So if we go back to the source of that, you can imagine a system of axes in your 3D space. Okay, so say this is your x, this is y, then this is z axis, the positive directions of these axes. Not caring about whether it's a right-handed system or left-handed, not thinking about those things, okay? So in this, you can imagine a vector, so which is emanating from the origin. It's like the position vector of a point. Suppose the point is 2, 3, 3. So it's in the first octant. Now you know that along these directions you have the unit vectors, which you denote by I cap, j cap and k cap. So here you are in fact looking at the vector space of 3D vectors, actual vectors, or in other words the Euclidean space R3. If you identify such triples with their position vectors with respect to some already given system of axes, some origin. Now what happens is that you can draw a perpendicular from the terminal point of this vector on the xy plane, and then what you can do, you can further draw perpendiculars from that point on the x and y axis. Okay, and what else you can do, you can join the origin also with that foot of the perpendicular. So then you will see that using your parallelogram law of vector addition, you get this vector itself. So we call it V. Okay, and I'm using that thing also because these are actual vectors, I mean physical vectors. So you can write you know how to write V in terms of these basis vectors. V is going to be equal to 2i plus 3j plus 3k. So if you want to find a vector that is, say, perpendicular to 2i plus 3j, just simply saying, okay, so what is 2i plus 3j? 2i plus 3j, if you look at this figure, then this vector which starts from here and ends here, that is 2i cap, and 3j is this much. So 2i plus 3j, because these are parallel and have the same direction, is this vector, which comes like this, starts from the origin and ends at this foot of the perpendicular from that point, from the tip of this actual vector. So then what happens if you say subtract? Am I really getting what I'm trying to say here? If you subtract 2i from this, then you have 3j. So from this vector, if you are subtracting 2i, then you get 3j. So that after you have performed the subtraction, the resulting vector is perpendicular to 2i. So what I am trying to say is that from a vector w, if you remove the amount of v1 that is along w, then the resultant is going to be perpendicular to w. It's like you have this vector from which if you remove its component, the vector will have components along the axis, right? So if you remove one component, then the resultant, whatever is remaining in the vector, that is going to be perpendicular to that direction, because in that direction it has nothing left now. Maybe my explanation about this whole thing is not that good, but at least you get the point that here what we are doing is that from W we are removing the component of W along V1, the component of W along V2, and all the other such components, so that whatever is left, that will be perpendicular to all these vectors, all these axes. So in this case, the orthonormal set is this set of vectors. You know that these are mutually orthogonal and they have length 1 also. Okay, because I have decided to bring this example suddenly, so maybe I messed up with this. Okay, so don't worry about that. Instead, let us now look at an example which illustrates this Gram-Schmidt process in a vector space which is not this, but which has polynomials in it as vectors. And the space that we are going to look at is the space of polynomials of degree at most 2, real polynomials, along with the 0 polynomial. So instead of formally writing anything, we are looking at this space. Polynomials of this form, where A, B, C are real numbers, any real numbers. One can very clearly see that this V is going to be a subspace of the space of all polynomials, all real polynomials, and in it we are going to use an inner product, which is this. Say you consider two such polynomials from V, and the inner product that you have is this. One can prove very easily using the various elementary properties of integrals that this is an inner product on this space V. Now, if one wants to say find an orthonormal set that is going to be a basis for V, then how would the Gram-Schmidt process go for this case? And the initial basis that one would take in this case consists of these monomials 1x and x square, which you can clearly see that we already know that this is a linearly independent set here, and you can clearly see that they span the space V. So this is the basis for V. So if one uses the Gram-Schmidt process, then W1 becomes V1 divided by its length Okay, now V1 is the constant polynomial 1, but do not suddenly just simply without thinking of anything write 1 here in the denominator also. Do not do that, because it's not 1. You have to use the definition of this inner product, that is, you have to calculate this, which is actually not 1. Oh, sorry, it's not simply the inner product, but rather its square root. One times 1, so if I do not write that 1, I get dx. And this, you can clearly see, you are going to get x as your antiderivative, and then 1 minus minus 1 is going to give you 2. So the vector actually is not 1 W1, but 1 over root 2. It is still a constant polynomial, but it's not 1. Then you of course calculate U2, which is this, and V2 is your x times 1. So if you write down the inner product, then it is this. Since x is an odd function, so this integral is going to be 0. So U2 is x itself. But now, in order to write W2, you have to divide U2 by its length. X times x gives you x square, and if you actually calculate it, you will see that you are getting square root of 2 divided by 3. That means ultimately you get this. And similarly, if one calculates U3, then it turns out to be x square minus 1 over 3, and calculating W3, you will say it will keep on getting complicated, but if you go through the full process, you will see that it turns out to be this. So although your original basis is very simple, very easy, consisting of the polynomials 1x and x square, the orthonormal basis is complicated, but still it is orthonormal, and that basis now looks like this. Keep in mind that when we say an orthonormal set, it means with respect to some inner product. So if the inner product changes, then this set may not be orthogonal or orthonormal, but with respect to our inner product, which is given by this integral, this is an orthonormal set of vectors in that vector space. So it is also a basis. You can see that just like the original basis, here also we have a constant polynomial, a linear one and a quadratic one, just like 1x and x square. And I am going to stop with this itself. I am a bit not happy about the fact that I wasn't able to say something useful about this example. I thought about it. Before starting the video, I thought about it, but I did not think through it properly. Maybe that's why I failed to say the things that I wanted to say. But at least you can, what I wanted to say vaguely is just this. If you have a vector, then from that vector, if you subtract a component of the vector, say you have this vector v, then its component along the x-axis is going to be what? That may be a question answer. No? We know that that is nothing but this. This is the effect of the vector along this direction. It's like when you apply a force on some object that is placed on the ground, somewhat at an angle, then the full effect of the force is not felt by the object. Only a component of the force helps it to move forward. It's like that. It's the component of v along x, which is this. Now if you remove that thing from v, then the resultant does not have any component along this. So this vector is going to now be perpendicular to the resultant, because the resultant is acting in this direction. So nothing about the resultant contributes anything in this direction. So that is why that u looks like this, and if you construct that u like that, then u is going to be perpendicular to all the vi's, simply because u has lost its influence in those directions. That way you can think about it. You can of course think about it and make it much more clear than how I expressed it. But anyway, that's just it for tonight. And tomorrow also we have our upload, and tomorrow we are going to go back to the exercises from Lee's algebra. So with that, I say goodbye for tonight. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.